and Eduardo is going to talk about soil creep, a statistical mechanics perspective. Thank you, Eduardo, for
Thank
coming.
you, Danilo. Good morning, everybody. I will present my work doing in collaboration with Ezequiel Ferrero in Bariloche, Argentina. And to motivate my presentation, let me first refer to a problem that people in the community of earth science, geophysicists, geomorphologists, etc., have been considering for a very long time, which is the problem of soil creep, in fact. This is what happens when you have a terrain that is inclined, a terrain that may be formed by some kind of sandy material or some terrain, any gravel, etc. And although you may think that this terrain is stable, I mean, it does not evolve over time, it happens that it does really, and over the years, typically it moves down, creeping slowly, and the indication of this is given by this kind of stick that people have dig into the terrain, and after some years they have come back and see what happened, and then see that this stick has been bending or even broken, and this is because over the years the terrain has creeped down, in fact, more at the surface, of course, and less in depth. And here there are few realizations, observations across the world that are normalized by some typical depth. I will not pay much attention to that, and also to a typical displacement, but when you normalize in this way, typically this creeping has this kind of exponential behavior. So, well, this is contained in this paper, actually, which was our kind of motivation to enter into this field, because here they say that probably this could be modeled or studied with the tools of statistical mechanic models, the theories of yield stress materials that I will refer in a minute what this is. And so this is what motivated us to enter into this problem. But in fact, to be able to say that this is a kind of yield stress material, let me explain what these kind of materials are. And for reference, let me just beginning with something that is very well known for everybody. It is the case of a fluid, not a yield stress material. A fluid, although maybe some very viscous fluid like honey that we have here, in a fluid, you have, if you apply the shear stress to a fluid, you obtain immediately some deformation velocity, namely the fluid deforms at a given rate, and this is precisely called, well, if this is linear, it's called a Newtonian fluid, otherwise it's non-Newtonian. But the point is that as soon as you put some stress, the material deforms until the shear disappears, or eventually continues deforming for a very long time. And this is what happens with honey, because if you pour some honey onto your bread, it will not stay as a cusp, it will spread out in some amount of time, okay? But if you take another material from the kitchen, you take cream, for instance, and you make a heap of cream like this will stand for a very long time, indicating that the cream is able to sustain its own weight, the shear stresses that its own weight apply to itself. However, it's clear, and you all know, that if you apply some stress with a spoon or something onto that, you are able to deform very easily. And this indicates that the deformation or the deformation velocity as a function of a yield stress in this kind of material have a kind of critical shear critical stress here. If the applied stress is lower than this critical value, the material behaves essentially like a solid, and if you apply a stress that is larger than that value, essentially behaves like a kind of liquid, okay? And there are many materials that behave in this way. There is a very nice picture taken from this review in which Ezequiel is also one of the authors. It's an indication of where you find this kind of materials. Essentially, these are typically materials that are in some sense granular, with a granular structure, and the classifying pattern here along the x direction is given by the size of the particles that form the material. You have cases in which these elementary constituents are very small, like in metallic glasses, etc. And you can go up to sizes, macroscopic sizes of the order of millimeters, as you have in in sand, for instance, with grains, or in a pile of rice, rice grains, etc. These are granular materials that behave like yield stress materials. And the other motivation to put this slide here is to show, to indicate that the effect of the grain size on the behavior of this material is, the thermal fluctuation have very different effect along this line. Because you have to compare the thermal energy, KT, you have to compare it with a typical energy here that will be probably, if this is just a grain of, a pile of grains onto the table, you have to compare it with the potential energy of moving a grain the distance of a radius typically. And for grains that are macroscopic, this is much more than thermal energy. So it means that thermal fluctuations is negligible completely in this limit. Probably it has some effect, maybe important even in this region, but not here. So if we think, or if we pretend that layer of soils can be described as a kind of yield stress material, granular material like that, I would say that soils are probably much more in this limit of the plot. And so for the soils, thermal activation is not important. I'm not saying that temperature is not important, just thermal fluctuations, okay? And the thing is, in fact, that these kind of materials, this is the plot that I put before, the formation as a function of yield stress. But if you think in the problem of soil creep, or even in more general abstract problems that people have been considering from many years, it happens that actually there are mechanisms that make this material to flow somehow below the critical stress. And these are named, or are called typically creep phenomena, and there may be different reasons for this creep phenomena. And one, we thought that probably this problem of soil creep is related to some way of creep that occurs below the critical stress that is indicated here. The point is, what is the kind of activation or the kind of creep that can occur for a layer of soil moving down a hill? So this is the question, and I already said that thermal creep, namely thermally activated motion of the particles, can have an influence in some materials, but we think probably, or people agree that probably do not have any effect in the case of soil creep. So this is not a mechanism that is reasonable to explain the phenomenon of soil creep. Geophysicists, geomorphologists have for a very long time known that mechanically induced creep, namely mechanical activation caused by a number of reasons that it can occur in this material, can produce this kind of creep, or this kind of behavior. If you take a heap of sand, put it onto this table, and you leave it alone, probably it will stay for a very long time. But if you start to tap onto the table, it's clear that it will slightly move down and flatten. But this is a dynamical phenomenon that can occur. I'm not denying its importance, but this is not the phenomenon we decided to study, because other people also said, and in many cases it was argued, that the other phenomenon that can influence this creep down of soils is something that is correlated with variations in ambient conditions in a general way. This could be, for instance, variations in temperature or humidity in the atmosphere that influence in some way the behavior of the system, producing some day-night variations, or even winter-summer variations that can produce this phenomenon. And actually, this is a very old, this is a sketch of the idea of this phenomenon. Let me start with that. If you take two particles, two macroscopic particles joined by some kind of hinge or something like that, resting on an inclined plane, and suppose we are below the critical angle, namely this is not sliding, this is stick because of static friction forces. But if we are able to control the value of this angle, for instance, some externally controlled mechanism that varies this angle, if I reduce this angle, the particle that most likely will move is this one here, because when I reduce the angle, the force that I apply onto the particles, onto this one, go in the same direction than the already pointing down component of the gravity acceleration. So when I reduce the angle, this goes to this configuration. And probably when I move up the angle again to the original value, what will happen is that this particle is the one that will move, because now the force for when opening this angle goes down for this particle and up for this one. So most likely this particle would move, and we end up after a cycle of variation of the angle in this new configuration that is essentially similar to the original, but actually is displaced by some quantity. So this kind of behavior, which does not imply, as I said, thermal activation, is a very silly, actually, very, very simple mechanism that can produce the movement down of this object. Actually, there are a number of toys that play this, make this mechanism to function in some way. And when looking to the literature, we found that the first reference to this kind of mechanism, the problem of movement, down movement of objects on inclined planes, is this very old paper by Mosley in 1855, where he describes the movement of plates of lead, I think it was, on top of roofs in some places, that after years he saw that they moved down, and he correlated it with the heating and cooling of this material along a very large period of time. And actually this, this is the idea that I will present here. This is the central point and nothing else. You cannot go now, but essentially all the ideas that we will present are related to this mechanism. But I show two different approaches to implement this kind of behavior in systems that are now extended with many degrees of freedom, with many particles, etc. Actually, it's a bit strange for us. Was a bit strange to not to find the development of this idea along the years that come after this original presentation. As far as we know, not many people has paid much attention to study this phenomenon in a quantitative way in more realistic models. So I will present two approaches to study this phenomenon. One is simple, let's say simple or direct molecular dynamic simulation. Then I will present some results on mesoscopic models. To start with a molecular dynamic simulation, what we did is to consider a granular material, essentially describing the material that is contained in this rectangle, which is a piece of the material that is supposed to creep down the inclined plane. We model this as a collection. We do a two-dimensional simulation of this. We model it as a collection of disks of different radius. And in fact, well, just a few details. I will not go into many details, but these disks are frictionless, just for simplicity, but essentially they can stay at rest at some inclination of this angle because of the interlocking of the grains, essentially. Of course, if you put an angle that is very large, this runs, the configuration runs away. I mean, you have an avalanche. But we start with a configuration in which this is stable, namely even in the presence of this component of the gravity acceleration, this would last, this configuration, forever if you do not do anything to the system. But what we did is, with the idea that temperature influences the system in some way, one can think, well, probably if you are changing the ambient temperature here, this influences the size of these grains, namely you can have thermal contractions and expansions. So we did the simulation considering that this is, let me put all together, that we start with this configuration with some distribution or radius of the particles, and from here to here, let's say we multiply the radius of the particle but by a function that is this linear profile here. So we are increasing the size of the particles at the top, mimicking a thermal expansion, and we consider that the effect decreases as a function of depth, so it vanishes completely here. So up to here, the particles are exactly as they were before, and from here we take a linear profile of modification of the radius of the particles. So when we increase the radius of the particles, the system swells, becomes larger. So this is evident here from the increase in the surface, the vertical surface here, and then we go back to the original configuration. The question is this configuration the same as this one here? The answer is presumably, because of all I said, presumably not. And the fact is that, in fact, it's not. I mean, here the dots indicate the original configuration of the particles, and the final configuration at this plot C are given by the tips of the segment that start on each particle. So you see that in a cycle of increasing and decreasing of the radius, the particles at the surface have moved the most to the right, and as we go deep into the system, they move less and less, and essentially where the radius didn't change, the particles remain in the same original position. So doing some statistics on this kind of simulation, we can construct curves that show to us the profile of movement of the particle. This is in units of the radius, of the average radius of the particle, that how much a particle at the surface has moved after one cycle, how much a particle at a given depth has moved after one cycle.
Very quickly, is this 2D or 3D?
No, 2D.
2D,
yes.
And what interactions, or do you have?
Volume
Just
excluded volume.
Okay.
As here, for instance, this is the profile that we use for the change in the radius, and different curves correspond to different amplitudes, some fraction of the radius itself. You see that essentially you observe the phenomenon in the region where the radius have changed, but there is also some interesting tiny phenomenon. I mean, below the value y naught here, some particles that are below even have a drag because of the particles that are above, even if their own radius didn't change, okay? And this is another case in which we take profiles of different forms like this, and we observe the profile of creep in the form of these three curves that are more or less exponential as the experiments indicate they should be. But well, here there are a lot of unknowns in the problem. I mean, we take this very simple linear profile of temperature. One should probably put a more realistic profile obtained with the with the equation given the temperature as a function of depth, etc. But we didn't go into much of those details. Well, this is a flavor of the result of the numerical simulations, and now before that, sorry, and because there are many people here that are interested in active matter, let me say that this kind of model, totally independently and actually before our work, was proposed, or some similar model to this was proposed to something that could be called an active system of particles. If you consider that these disks, in fact, increase and decrease the radius, but not all together at the same with the same phase, let's say, but typically one with different phases, namely the same period but different phases, you have a system in which the particles are changing size. Where is it? Are changing size for instance, from this configuration. This particle increase in size and then decrease, but others probably here decrease the size up to here and then increase. So this is not in phase. But it happens, I mean, these people show that it could happen that after a cycle of variation of the radius, this particle can probably not turn back to the original positions, but turn to another position. And in fact, if the amplitude of the oscillation of the radius is small, typically all particles return to its original position, so the material continues to be a solid, let's say. But if the amplitude of the oscillation is larger than some critical value, then after after a cycle, the particles move to another position, and if you repeat this again and again, this continues to change over time. So this was called a kind of fluidization transition induced by the change of the size of the particles. So for anybody interested, this is a nice paper. So to go to the second kind of modeling that we've done concerning this problem, these are cases of what we call mesoscopic models that we have been using for a long time to describe transitions like what we call depinning or yielding transition in materials. Actually, this was our field of study for many years. I cannot go into all the details of this field, but actually we have applied it to many different physical processes. Anybody that is interested in some of this, we can discuss in particular. But to give a flavor of the kind of modeling that this is, let me consider the simplest case, which is the case of an elastic string, which is essentially an elastic variety moving onto some disordered potential that will have some physical interpretation depending on the problem. But the point is that you have to drag this line on top of this potential, and it seems pretty clear that because of these highs and lows of the potential, if you apply a very low force, you will not be able to displace the string. By the way, the equation that I consider the equation of motion is an overdamp dynamic equation. So in principle, if the potential is not here, I apply a force and the string moves. But if there is this potential, I have probably to overcome some minimum force to be able to go onto the potential barriers. So the dynamics of this kind of model is, in fact, given by this kind of equation, overdamp equations of motion. These are the coordinates, whatever it is, that represent in this case the position of the string, but maybe other variables. And the forces onto each particle, it is the external force that I apply onto the whole system, the force created by the disordered potential that, as I said, may have different physical origins, and this force, which is the elastic internal structure of the string or the manifold that we are considering. This is the quantity that will give us idea of the physical process we are modeling, and to give some kind of examples of what this could represent. Let me first say that typically we work in Fourier space, so this force that depend on typically the difference between coordinates I and j, we transform to Fourier space and describe as in terms of g of q. For instance, if we take g of q to be constant, literally constant for all q, this means that the interaction in real space is independent of the distance, and this is a kind of mean field limit of the model that is in many cases very useful to get some analytical results, etc. But if I take instead, for instance, the case of a g of q that is q squared, this is the Laplacian, and when we go back to real space, this is an interaction that is near its neighbors, and it's essentially, for instance, the situation with an elastic string with local elasticity, okay? And for us, for our problem of soil creep, it probably will be interesting to consider this more or less like describing the situation of a solid body. I mean, the body itself here cannot deform, but the interface between the body and the resting plane is, of course, not completely flat. It will be rough at some level, and it will be elastic. And so the line that I was plotting before, this line that is here is essentially representing the evolution of the interface between these two bodies here, okay? And the third case that is important for our description is what is called the yielding situation. Here, the yielding situation is described in terms of an elastic kernel that gives the elastic interaction between two particles deforming, I mean the strain in 2 points of an elastic system deforming and interacting. The exact form is not important for the details, but the point is that essentially this describes the yielding transition and is able to describe how, I mean, in this case, x and y are the two coordinates in this plot, and this is able to describe how this body deforms plastically upon the application of a given stress. To give you an idea of how this happens, let me show the situation, for instance, when you take a sample that is a square, and it's compressed in this direction and expanded in this direction. This is what is called a deviatoric strain. In this case, the pieces of the material will resist the deformation, but at some point, because this is formed by grains or things like that, at some point these grains can reaccommodate locally and deform, and this is taken into account in the model by in fact the disorder potential that I mentioned before. When a piece of material deforms, it produces an elastic disturbance into the system that is observed in the values of the strain. These are plots of the values of the strain, averaged or integrated in some period of time upon the deformation. These are spots where the material is locally deforming. And if you see that after a while, if you integrate over a longer period of time, these deformations interact and try to form a kind of a structure with lines along the diagonals, which is the natural expectation if you compress this in the horizontal and expand into the vertical. You expect that the sample fails or slips along planes in the diagonals in one direction or the other. However, in the long run, the system has a deformation that is essentially uniform. This means that this is precisely representing a case in which the material deforms homogeneously. And I will go back to that curve in a second. So in this case, if we apply to our problem of soil creep, actually there is a difference here in considering a deviatoric deformation, which has the two single stresses, single shears. In the case of one single shear, we would obtain this kind of deformation into the material. Okay, but this is the reason why this model could say something about the dynamics of soil creep. Actually, one point to be clear about this, the simulation that I will present for the yielding model will not describe the full situation at every horizontal plane, but will describe the situation in a given spot of the material at some depth, let's say, and they are homogeneous simulation. They do not describe the full situation all across the system. But the important thing is that in any case, in this material, whatever x is, and as for this case, x is the strain deformation into the system, the velocity of deformation, this large X is the average of X overall system, the velocity of deformation as a function of the stress has in fact a form that is that of a yield stress material with a critical stress that is given here. So the idea with this, in fact, was to consider this kind of models and see the effect of changing of a global parameter into this kind of flow curve, namely in the forms of the. So it's stuck. It didn't work. Oh, what happened? Okay. The point I want to stress is that. Okay. If I consider the system for a given value of this constant k essentially is the overall value of this strain kernel. I mean, if I increase k, it means that I make the system more rigid. If I decrease k, I make the whole system softer. As I said before, probably what we could do to make a model of the soil creep behavior, we can change this value of KL from a large value KL to a small value KS and see what happens. The idea is that there's something that is wrong. Um, hmm? No sé.
Just a second. Right.
Okay. Yep. But mhm. Probably reinitiate. Up, up. Mhm. That is doing all clicks together now. Well, now seems it's working. Huh? Sí, sí. In principle, it's me. Okay. So if I change this value of k between a large value and a small value, we expect that the flow curve of the system moves, as I said before. Actually, for a small value of elasticity, the critical stress is larger because the system can accommodate better to the disorder potential. But the non-trivial finding that we obtain is that, in fact, when cycling between a large value of the constant k and a small value, in addition for this curve moving rigidly from one to the other configuration, we obtain a global displacement of the system in a quantity that is just a fixed value of the typical variable x. And of course, this depends linearly with the number of cycles that I do on the problem. So this is nothing more essentially than what I described in the toy model here. This delta x is nothing more than the displacement of the toy from here to this configuration. Let me just have a very naive explanation of the phenomenon for the case of the pinning, the case of we have an elastic string on top of the potential, and what happens with we change, in fact, the elasticity of this spring. Consider that this string is formed by the points that are indicated here. They should be thought to be joined by springs. And the potential, this random potential here is implemented in a form that consists of a very well-localized potential wells and some regions that do not have any potential. So in a given configuration for a given value of the spring constant, probably this is a configuration of the system, and this line indicates the mean position of the string. If I reduce the value of k to a small value, and you can think of a value that is essentially zero, if I take the interaction between particles to be zero because of the force that is applied onto the particles, all particles that were in between potential wells will move to the next available well at the right of the particle. And now the system is at the red dots here, and the mean position is the dotted line here. When I go back to the original value of spring constant, essentially what happens is that the particles that jump to new potential wells are not able to return to their original position, but those particles that are leftmost in the plot are those that feel the largest force, and some of them jump to new positions to the right, and now the average position of the system is here, which is shifted with respect to the original position, although the value of the spring constant is the same here and here. The system has moved, has deformed, okay? So what remains is just to show the result of numerical simulation that are nothing, I mean, the interpretation is just the one that I have given already. For instance, for the pinning, we have here the flow curves obtained at different values of the spring constant, but these are the standard curves when the spring constant is kept constant, is constant over time. And in fact, you see that there is a critical value of stress, and from here the system deforms. If I take one of these curves, for instance here, the one corresponding to this value of K, and I produce this cycling effect, reducing K to a new value, K small, that is indicated here, and then back to the original value, and in this way many times, what we see is that below the value that was the critical force here, 0.14 more or less, we obtain a displacement of the system that is in fact linear with the number of cycles into the system. The other point that is interesting to notice is that this behavior does not persist up to zero applied stress. I mean, it appears, and it was a surprise for us, to see that it appears a kind of new critical stress, that is the value where these curves go to zero. And if we have an applied stress that is below that value, the system, even in this regime of oscillatory spring constant, the system does not evolve. Okay, the results for yielding are essentially the same. There are simply some qualitative differences in the form of the curves that is a well-known behavior for people working in this kind of problems. And also we did, in fact, this also for the mean field results, which are interesting in the sense that we have some analytic clues or results that can be used to interpret this. The flow curves in the case of mean field results are known to analytically to go to zero linearly, and this is in fact what we observe here. And when we cycle the values of K between a large value and a small value, in fact, the evolution of this delta X is also linear close to the new critical stress that we obtain here. And actually, we have been able to obtain some analytic form of these curves in this case, indicating that, in fact, this new critical stress is an analytical feature of the problem. And this is quite interesting because the existence of this new critical stress, we think, is correlated to a phenomenon occurring in another problem, which is in principle different, but in the end probably very related to this, which is the problem of fatigue crack propagation in materials. If you have a metallic piece of material or something like that with some pre-existing crack, and you apply a stress onto the material, of course, if you apply a very large stress, you will break the material. But if you apply a stress that is small, typically the system is stable. But if you start to increase the stress and decrease the stress, even keeping all the stresses below the critical stress for running out of the crack, but this oscillation of the stress produces the increase in the length of the crack a small amount every cycle. This is well known in application, has many, there are many, well, it's a well-known phenomenon, very well studied. And we think that this, in essence, this kind of modeling that have been presented is in some sense similar to this problem of fatigue crack propagation. Here we have this change in the elasticity of the springs on this mesoscopic model, and even if at a constant value of the spring, the system would remain stable and fixed forever, when you do this cycling, the system evolves a small amount in every cycle. And in fatigue crack propagation, there is an interesting case, an interesting phenomenon that is called the sorry. So it's sorry about this. It's called the endurance limit of fatigue crack propagation. There are materials that, for crack propagation, that if you apply a cycle of increase and decrease of stress that is lower than some critical value, the crack does not increase anymore. So there is a kind of limit between the possibility of crack propagation by fatigue and the case in which this crack does not propagate, and we interpret that here we have the same phenomenon in which here the system is evolving if we apply a cycle of, if we cycle the values of K between some two values in a given range, and if the applied stress onto the system, the overall stress is lower than a given value, then the system does not evolve at all. I will skip this part. It's not very relevant here, and I will pass directly to the summary. So we have made some kind of modeling for the study of subcritical thermal creep that can be driven by variations of system parameters. The system parameters in our case have been the radius of the particles in the case of the molecular dynamic simulation of the stiffness, essentially, of the elastic object in the case of the mesoscopic modeling, and this with the idea of have something to say for the effect of temperature or humidity oscillations on the properties of soil creep. We have obtained that creep is larger, close to the critical value sigma c, and also we have obtained that this creep vanishes below this new critical shear stress sigma naught that we have identified, and we have obtained behavior of this quantity very much like, as I said, the endurance limit of fatigue in fatigue crack propagation. Well, so this is all I have to say. Let me just congratulate the organizer for a very nice meeting. Thank you for the invitation to participate here and being in Sao Paulo for the first time. And of course, thank all of you for your attention.
Questions for Eduardo? Yeah.
I don't know, it seems a little bit similar to like a ratchet mechanisms that you have, but of course you're in the overdamped limit, and in the ratchets you would have a diffusion. But there is some similarity, no?
With that, you said, sorry, with the
ratchets.
Yes, it's a sort of ratchet in some sense. Yeah, I mean, it's more or less clear. I mean, of course, it's something that is completely out of equilibrium. This is not. Yeah. This does not occur in equilibrium, but this kind of toys, as I said, that have two legs and you change temperature and then start to move in one direction, actually in one direction, or even they can climb some slope, is a ratchet mechanism, absolutely, yeah. Well, the fatigue crack propagation is a kind of ratchet phenomenon. Right. Mm-hmm.
Thank you, very interesting talk. You motivated your talk with the involvements in soil. Mm-hmm. How difficult would it be to actually adapt your simulations to real like soil morphologies?
Probably very difficult, at least for me. Actually, we are used to toy models or very simple models, and this is what we have done. And in fact, to say more about realistic situations of soils could be very difficult. Probably the situation of a pile of sand, dry sand, etc., could be more or less simpler because you have control over the distribution of particles, etc. But if you take a soil that is like the one that you see here, there are a lot of variables, and I do not really see how do some more realistic simulation. This is a kind of proof of principle that this kind of mechanism can work, and that is all I can say.
Yes. You had a very suggestive picture, 3 pictures in fact, when you have shown the slide about deviatoric stress. Can you project them again, please? Because they, what is the origin of the black and white or the gray level contrast? It was much before that.
Which one?
Yes.
Ah.
Yeah, exactly that. So the
This
point
is
is that. Oh yes, go on.
Yeah, I'll explain in more detail. This is what happens in fact in a sample that is original this and you deform in this way. Here we are plotting the deformation with respect to the average deformation. Actually, I'm plotting the delta of the strains at different points to emphasize the situation in which different spots have deformed in one way or the other. It is not indicated here that the sample have deformed globally. I mean, the sample continues to be square in these plots, but actually, if I have to be realistic, I should say that here the sample has already deformed to something that is, okay, has decreased the size in this direction and increased in this size. But the idea of this plot is to show the heterogeneous strain deformation into the sample, that eventually, if you average over a very long period of time, these heterogeneities become less average out in a very long simulation. But individual spots are very clearly seen when you do this. This corresponds to rearrangement of local rearrangement of particles that produce elastic interaction that have this typical quadrupolar form. That is what is encoded in this SLB kernel that I mentioned. I don't know if this addresses your...
Yeah, the point is that your figures are very clearly reminiscent to what is observed in optical microscopy between cross polarizer when you are looking at defects in lamellar phases, smectic.
Well, probably,
systems.
I
So
mean...
it hints at layered structure or something underneath. So
this
you
is
have spherulites, and then you have oily streaks or things that are quite...
Well, actually, the different color here is the strain state at different points, which is actually what some these optic techniques look, I think, when you observe with a microscope. But you have to think that here the level of white, between white and black, is the strain state of each point, with reference to the average strain of the sample. Okay, so it means, for instance, that white regions are less deformed than the average of the sample, and black regions are more deformed than the average. And here, for instance, you see the correlation in these regions. There are regions that are more deformed, forming kind of lines, and there are other regions that are less deformed. But on average, the average color of every of these samples is the medium gray that is there. But I agree it's correlated with these images, because the microscope images, in fact, see the strain state of the sample. No?
Thank you.
I have a quick question myself here, Eduardo. Yeah.
Sorry.
In the pinning case,
yes.
What's the pinning scenario? Is that collective weak pinning, where you have?
I mean, you can do it for different forms of this pinning potential, but typically we think of uncorrelated short-range pinning, namely not. This could be probably produced by uncorrelated pinning centers, and the overall, I mean, then sum up to some typical disorder potential that has some properties. They can be long-range correlated, but usually we consider the case of short-range correlation of the potential.
I was just wondering, I remember reading lots of theory papers dealing with collective weak pinning and finding results, and I was wondering whether it was possible to combine those theories in some sense.
I mean, people have made a lot of work about this. There is a huge field, and in fact, there are different universality classes depending on the correlation of the disorder, or or even the elasticity of the manifold being short range or long range. there is a zoo of behaviors, actually.
Okay, okay. More questions? Pablo has a question.
So
Yeah.
I imagine that about the first part,
Yes.
if the granular matter is dry or wet, the swelling would be quite different, right? Because of water bridges, water inside the grains, so on and so forth.
Probably.
Has anyone measured this swelling?
I'm not aware, at least, I should say. But probably here there are some indications for something to be measured that could correlate this behavior with, in fact, with the change of humidity, etc. But I'm not aware of any results along that direction.
Chantal.
Hi, very nice talk. Thank you much. Related to similar question, I seem to remember that there are colloidal particles, are called microgels, that actually, depending on the temperature, they can swell or shrink. So, and people such as Dave Wade studied actually the behavior of the microgel, very, very dense suspension. That depending on the temperature, this system can change from a fragile to a strong glass. Would a similar system, it is true that it's not, the same, but these particles at least they can swell with temperature. So maybe an experiment with a temperature gradient could be used to...
It's a very nice suggestion. Yeah, I think that this could possibly be implemented. I mean, if you can make some material that is in principle rigid, but if you can make the particles to swell, etc., probably under some shear stress, you can observe probably something like that. Yeah, I think so.
Okay. Thank you.
Yeah, this is a very nice idea. It would be much easier to experiment with that.
Okay, let's thank Eduardo again.